Okay, here we are coming up on week 4 of our conversation about complexity and justice during the summer of 2022. And this is going to be the first half of a set of, I'll try and get these both out to you today, but as you can hear, my voice isn't what it ought to be, so we'll see whether I can actually do this. So we're talking about complexity and justice. We are examining what it is that we mean by a complex system. And let me go over here. I want to remind you that complexity is what we see as just sort of the near edge of chaos. So reality, we know if we really pay attention, that reality is chaotic. What we really want to do is to have things be simple. If I have a simple way of understanding things, then I can know how to relate to it, and I can be guaranteed that if I do what I need to do, it's going to work. There is a best practice. But some things are actually not that simple. They're actually, where'd my cursor go? They're actually complicated. Because there's a whole bunch of simple steps, and I've got to do them well. I've got to do all of them well. I've got to do them in the right order. But if I do them all well in the right order, I will get what I'm trying to create. The problem with complicated is that there are all of these steps, and some of them change. If I do one thing differently, it changes something else. Complex is what we see when we have multiple interdependent variables. And so when I change this, it changes that. And so I can't really predict with any kind of accuracy what it is that's going to happen. So it's very hard to get our heads around complex. We can pretty much do it with complicated, and we'd love to have things be simple. But the other thing we're trying to do here is we're trying to get as close to reality as we can, right? So this zone between complicated and chaotic is what we call complexity. But I want to make sense of what it is that's going on for me, because the more I can make sense of what's going on, the better the choices I can make in how I show up in the relationships that I form, such that in the context of that relationship with you, we are creating what we all need, and thus what everybody needs, and everybody benefits from that. So that's why we have to be able to think in complex terms. So we want to be able to up our game here. We want to be able to move towards being able to use the best possible maps that we can. Now, remember that complexity is about the map. It's not about reality. You know, reality here is what it is. It's not going to change. The maps, we can have different maps. We can have different ways of making sense of things. But I have to pick a map that I know I can actually make sense of. Like when I look through this lens, I can understand something. So it's about finding better maps, but it's also increasing our ability to use the maps that we have to the best advantage, so we can as fully as possible know what is real, so we can make the best possible choices. So we use these maps in order to solve problems. So this was a problem that some artist came up with and had this installation over at the St. Louis Art Museum, and I've shared this with you before. This is a plexiglass cylinder that's probably 6 feet tall. I don't know whether it's plexiglass, but it probably is. And it's probably water in it, and there's a pump, and there's a hose that goes from the pump up to the top, and it squirts the water in. And what happens is that the water, both by being sucked out the bottom and forced in the top, causes a column of water to begin to spin, and spin fast enough that it actually forms a whirlpool down the middle of it. The centrifugal force forces it to the outside and causes this whirlpool to form. Now, if you're the artist / engineer that's trying to design this, you discover there's a bunch of things that you got to figure out. There's a bunch of things you have to be able to balance here. For one thing, the container has to be big enough. You have to have enough mass of the substance in it, probably water, that spins fast enough that you can get the whirlpool to form in the first place. Which means you have to have a container that has as few edges as possible. You don't want to create any kind of turbulence here. And you want people to see what you created. So you have to make a cylinder that's the right diameter, the right height, the right volume, and made of the right material so that it works for people to be able to see it. Now the pump that you use, it has to be powerful enough that it's going to get this column of water spinning in the first place. So how big a pump does that have to be? And if it's too big, it's going to create turbulence. And if it's too small, it's not going to have the power to get the water spinning. And so how big do this, and not just how much force, but how much flow. So how big is the tube have to be to carry enough water at the right velocity to make this work? Okay, now, as I said, it's probably water, and that's nice because water is relatively cheap, but it's got to be the right viscosity. We know water works because we see whirlpools on our drains when we're draining stuff out. The thing about the water pool down the drain is that as soon as the water's drained, the whirlpool stops. So the artist wanted to make a perpetual whirlpool, which that means it's got to be the right viscosity with the right power of the pump in the right kind of container. And she made this work. Because we see, as I said, I wish I had a video of this because it's much more exciting when you can kind of see the whirlpool dancing. There's one other piece here that I want to point out before we go to the next slide, and that is you really can't see it, but down there, kind of on the left side, right at the wall behind the white box that this thing is sitting on, there's an electrical cord. Yeah, the pump's got to get plugged in, right? It's got to have some power to run, which means this is not the closed system that it appears to be. If you unplug the pump, the whirlpool's going away. Okay, so there are some laws and language. This was one of the 9 things that we talked about in terms of aspects of complexity from last week. So laws and language. So the law here that's relevant is what's called the laws of thermodynamics. And in particular, we're going to talk about the second law. But the first law of thermodynamics is that matter and energy are conserved, which is to say that you can turn matter into energy, or you can turn energy into matter, although that's more difficult to do. But you can't get rid of it. It exists in one form or another, right? So we try to do this with producing electricity, with creating bombs, fusion and fission. We've got fission down. We can blow things up. It's trying to put together something is harder to do. When we master that, that'll be great. When we can do that, we can take garbage out of the trash and put it in our fusion engine and fly off into the future. But we're working on that one. So matter and energy are conserved, and this is fundamental to what we understand, the kind of the classic definition of relativity, the theory of relativity, which nobody really understands. I don't think even Einstein does. But in any case, E equals mc squared. Energy equals m, mass, times c, the speed of light in centimeters per kilometer squared. Which basically means that if you've got a little bit of matter, you can create a whole lot of energy. So this relationship between energy and matter is something that we're going to look at next week, because we started the world that we live in is a world of matter, of things, of objects. And that is, in one way of thinking, a very dense form of energy. As we move into more rarefied forms, we get less, it's less material, but it's more energetic. Okay, I guess again, I'm just flagging that because we're going to come back to that. Okay, but around language here, entropy is what happens to a system when it is a closed system. Order in the system will dissipate. So the example most of us know about this, if you got a glass of water and you put a drop of ink in it, you see the drop of ink. But over time, the ink, if it's water-based ink, it will dissolve into the water, and the water will just be sort of cloudy. And I can remember hearing in high school that, theoretically, for that drop to come back together again is statistically so incredibly remote. And actually, that's not true. It could never happen, because that would violate the second law of thermodynamics, which is that closed systems will experience a rise of entropy, which is the rise of disorder, in effect. Things are not separated anymore. Okay, now this is a problem for us as a nation, because is, well, if we close our borders, we don't have new immigrants coming in, we don't have that new energy coming in, that will actually harm. And studies have shown this scientifically. But if you think, oh, those immigrants are going to come in and they're going to take our jobs, the jobs that we don't actually want to do ourselves, we feel like that's dangerous. The danger is to not have open or semi-open borders. Nobody wants wide open borders, but they have to be semi-permeable so that people can come and go. So that the system, which is the nation of the United States, as I'm thinking of it here, actually has that source of energy coming in. So this is one of the ways that we can use the science of complexity to understand how it is that we can make choices that work better for us. All right? Because of this, one of the phenomenon that we see is that systems that begin to lose energy will adapt to the edge of chaos, that they'll make changes. And we're going to talk in a little bit about complex adaptive systems. But the adaptation will be to move towards chaos, not to become chaotic, but to get close enough to it that we can kind of pick up some of the energy from that chaos. We see this in people who are depressed. People who are depressed will look for chaotic activity to give them kind of a jolt. They'll know they're alive. They're going to bring some energy, some drama into my life. Okay? Now, one of the 9 aspects of complexity that we talked about is emergence. So emergence is what arises within a complex system when there's something that's brought to a structure within the system that allows it to move to a higher order of being. We talked about this in terms of fire. When you have fuel, heat, and oxygen, you bring them together, what you'll have is fire. Another example of this is if you have little dots of ink on a page and you bring them together into a particular shape, what you're going to have is a letter. And it's all the same dots, but when you have the letter, when someone looks through the lens that allows them to interpret the meaning of that letter, they say, oh, that's an A, or that's a Z. Right? I can see what that letter is. And that is an emergent meaning that comes out of the material of ink and paper, or ink and monitor, whatever, it's pixels, whatever. But we're seeing a contrast there. And so that arises and it has meaning. But look, this letter, that right next to it, there are other letters. And we look at all these letters together and we bring our interpretive map to that. Makes cognitive sense. Oh, that's a word. Whoa, that word has way more meaning than the letter does. Mostly. Sometimes there are letters that have lots of meaning, but mostly it takes several letters to make a robust word. And even some of the words, oh, is that read or read? Or I don't know. What? Sometimes we can't tell what the word is until we see it in the context of a sentence. Wow, look at all the meaning we've got now, and we've got a whole sentence in a paragraph, in a section, in a book, in a library. And at each level of emergent meaning in this case, what we are constructing is a hierarchy. And so what we see in complex systems are naturally emerging hierarchies. These days hierarchies get a bad name because we don't like dominance hierarchies, but systems are made up of hierarchies. That's part of what systems are. So we're going to talk more about that in the next video here a little bit. So we want the piece that I want to say here is that at each level in the hierarchy, not only do we get this emergent quality, those qualities operate according to certain laws. So if you have a bunch of molecules of H2O, right? If you only have one, it's just not a molecule. If you put them together, you get enough of them. Now you have liquid or gas or ice, or depending upon how it comes together. If it's coming together in a particular state, which is water, now it has the quality of wetness. A molecule doesn't have a quality of wetness. That only arises when you get enough of them together. So these emergent properties also have emergent laws that govern them. So I just want to suggest one way of using the science that comes up in this sense, the science of complexity. This is something I read on a blog post from the Santa Fe Institute. That's that group out in Santa Fe, New Mexico, that really looks at the science of complexity, tries to make sense of things, and tries to adapt it to who we are and how we function with each other. And this blog post was about if you're a part of a team that's going to hire folks, and or you had a vacancy on the team and you need to replace somebody, you're going to have certain standards of competence. Nobody is going to be in this job who isn't competent to do certain tasks. But once you've winnowed the pool and you've now got 6 people left who all are competent, now how do you decide? And their advice is pick the person who will make the team the most diverse. Because what you're bringing into the mix now, one person is not diverse. A team can have diversity. And the more diversity you have in the team, the more energy. It's kind of like adaptation to the edge of chaos. Whoa, this is novel. This is new. We didn't see this before. And the capacity to have that divergent perspective gives the team more energy and thus more creativity. Okay, so I'm going to see if I can get the second video out today. My voice is, I don't know what it is, but it's not doing very well. I'm going to at least get this one out to you. And if you don't get a second one today, it'll be coming tomorrow. All right, take care.